quick. Picture a busy street corner and just watch people walk past for a minute. Believe it or not, you're already watching a mathematical law play out. Here's the thing you've probably noticed without ever naming it. Measure a bunch of adult heights, or weigh the same bag of flour on a scale 10 times, or check how full a machine fills each coffee cup. And the numbers pile up around some center, then taper off on both sides. Few are very high, few very low. Most are right in the middle.
Right, and the remarkable part is they pile up in almost exactly the same shape every time, a smooth, symmetric bell. That shape has a name and a formula, and it's the single most important curve in all of statistics.
So, Week 3, Lecture 10, the normal distribution. We'll meet the bell curve, learn to read it with one table, and by the end, you'll be able to turn almost any what's the chance question into a quick lookup.
Let's get into it.
Quick warm-up before the bell. The simplest continuous distribution of all, where every value is equally likely.
That's the uniform. On an interval from A to B, the density is just a flat line at height 1 over B minus A.
Right, just a flat shelf. And 0 everywhere outside the interval. The variable simply never lands there.
Its mean sits right in the middle, A plus B over 2. And the variance is B minus A squared over 12. A flat-topped rectangle of total area 1. That's the whole story.
Easy enough. Now the interesting one. Here's the star. This is the normal density.
N of x, mu comma sigma, equals 1 over root 2 pi sigma times e to the minus x minus mu squared over 2 sigma squared. Don't memorize it, just notice it's that bell.
Yeah, don't let the formula scare you. It's defined for every real number from minus infinity to plus infinity, and it's pinned down by just two things, the mean mu and the standard deviation sigma.
And it earns the title, the most important distribution in all of statistics. Heights, measurement errors, test scores, averages of almost anything, they all tend toward this curve.
It really is everywhere. We write x is distributed n of mu comma sigma, and we say x is normally distributed with mean mu, which is its expected value, and standard deviation sigma, the square root of its variance. So what do those two numbers actually do to the picture?
Good question. The mean, mu, is the center. The peak sits right at x equals mu. Picture mu and sigma as two sliders in a photo app. Drag the mu slider and the whole bell just glides left or right. Same shape, never reshaping. That's the top pair of curves.
And the sigma slider pinches or stretches the bell. A small sigma gives a tall, narrow one. A large sigma, a short, wide one. That's the bottom pair. But here's the catch. The area underneath always stays exactly 1. So it's like a fixed ball of dough. Roll it out wider and it's forced to get thinner. Same total probability, just spread over more room.
Ha! The pizza dough rule. That one sticks.
For a continuous variable, remember probability is area. So the chance x lands between A and B is the area under the bell between them.
Formally, p of a less than or equal x less than or equal b is the integral from a to b of the density.
But here's the snag. That integral has no elementary antiderivative. You can't just find it with calculus tricks. So instead, we read the area off a table.
Right. This is where ordinary calculus tops out. And one area we always know, the total under the whole curve, from minus infinity to plus infinity, is exactly 1. It's a probability distribution after all.
A table for every possible mu and sigma would be infinite. The fix is one special bell that does all the work.
The standard normal, capital Z distributed n of z, 0, 1.
Mean 0, standard deviation 1. Centered at the origin, 1 unit out is exactly 1 sigma.
And here's the trick of the whole lecture. Every question about a normal distribution gets converted into a question about z. One table, and we're done.
That's the whole game, right there. So how do we convert? We standardize, subtract the mean, then divide by the standard deviation.
And here's the term for it, the z-score. Z equals x minus mu over sigma.
And the fact that makes it work, if x is normal with mean mu and SD sigma, then z is standard normal. A z-score just counts how many standard deviations you are from the mean, positive above, negative below.
Above or below average. Got it. Let me show you why it's allowed, because it's really a one-line idea. Start with the probability x is between x1 and x2.
Okay, walk me through it. Subtract mu from all three parts of the inequality. The probability doesn't change. It's like sliding a ruler an inch to the left. Every mark now sits over a different spot, but a 1-inch gap is still a 1-inch gap. We've just shifted everything by the same amount.
Love that. The ruler trick. Then divide all three parts by sigma, which is positive, so the inequalities still point the same way.
And look what's in the middle now. X minus mu over sigma. That's exactly z. So the whole thing became p of z1 less than z2, which the table gives as phi of z2 minus phi of z1. Any interval on x becomes an interval on z.
Slick. Same probability, brand new units.
Let's do one. X is normal with mean 50 and standard deviation 10. What's the chance it lands between 45 and 62?
Classic. Standardize each end. The lower one. z1 equals 45 minus 50 over 10. That's minus 0.5.
And the upper? z2 equals 62 minus 50 over 10. That's 1.2.
So the probability x is between 45 and 62 equals the probability z is between minus 0.5 and 1.2.
Which from the table is phi of 1.2 minus phi of minus 0.5. The big cumulative area minus the small one.
That's 0.8849 minus 0.3085, about 0.576. Roughly 58% of the values fall in that range.
And the calculus we couldn't do. Totally bypassed. Let's make that table concrete, because it's the one tool you'll use over and over.
The table gives the cumulative area to the left of z. That area is the cumulative distribution function of the standard normal. We write it phi of z, and it's just p of z less than or equal to z. The row is z to the tenths, the column is the hundredths digit.
Phi. Good to know the name when you see it. For an interval, you subtract. P of z1 to z2 is phi of z2 minus phi of z1, exactly what we just did.
And because the curve is symmetric about 0, two shortcuts. Phi of minus z is 1 minus phi of z, and the area to the right, p of z at least z, is also 1 minus phi of z.
So really, two cumulative lookups and a subtraction answer almost any question about a normal distribution. That's the whole skill.
Two lookups and a subtraction. That's it.
Let's actually find a value in the table. The tenths pick the row, the hundredths pick the column.
Say you want phi of 1.20. Go to the row for 1.2, slide over to the column for 0.00, and the cell reads 0.8849.
There it is. Now phi of 1.25. Same row, 1.2, but now the column for 0.05. That's 0.8944. The hundredths digit is the whole reason there are 10 columns.
And if your z is negative, either flip to the negative z page or use symmetry. Phi of minus c is 1 minus phi of z.
Symmetry to the rescue. Every question about a normal distribution is really one of three shapes, and they all come from that one cumulative table.
First, a left area, p of z less than or equal a. You read it straight off the table.
Done. Easy. Second, a right area, p of z at least a. The whole area is 1, so it's just 1 minus the left area, 1 minus phi of a.
And third, between, p of a to b, which is the big left area minus the small one, phi of b minus phi of a. Left, right, between. That's the entire menu.
Let's read the table on a real one. A certain battery lasts on average 3 years, with a standard deviation of half a year, and lifetimes are normal. What's the chance a battery lasts less than 2.3 years?
Nice, a real-world one. So mu is 3, sigma is 0.5, and we want p of x less than 2.3.
Standardize. Z equals 2.3 minus 3 over 0.5. That's minus 1.4.
So p of x less than 2.3 equals p of z less than minus 1.4.
Look up minus 1.4, row minus 1.4, column 0.00, and you get 0.0808, about an 8% chance, the little tail on the left. A word problem is just standardize, then read the table.
And for the manufacturer, that 8% is warranty claims and customer complaints. Real money.
And if you'd rather not flip through a table, GeoGebra's free probability calculator does the continuous normal directly. Pick normal, set the mean to 3 and the standard deviation to 0.5. Choose the less than interval at 2.3, and it reads back 0.0808, exactly our answer. Drag the boundary and the shaded area updates live, which is a great way to build intuition for what the table is really giving you.
Same answer, zero arithmetic. But the table's the one that teaches you what's going on.
So far, we've gone value to z to area. Sometimes you need to run it backward. You know the probability and you want the cutoff value.
Ooh, reverse gear. That's a critical value, written z sub alpha. It's the value that leaves alpha in the upper tail. P of z at least z alpha equals alpha.
To find it, convert to a left area. If alpha is in the right tail, then 1 minus alpha is to the left. Now you read the table in reverse. Instead of using the margins to land on an area, you scan the body for 1 minus alpha, a bit like a game of Where's Waldo, then trace back out to the margins for the z that produced it.
Where's Waldo? I love it. So it's the same table, run in reverse. Forward, value to z to area. Backward, area to z to value.
Let's do one. Find z sub alpha so that the upper tail area is 0.34.
So we want P of z at least z alpha equals 0.34.
Flip it to a left area. P of z less than or equal z alpha is 1 minus 0.34, which is 0.66.
Now hunt for 0.66 in the body of the table. The closest entry is 0.6591, sitting at z equals 0.41.
Closest we can get. Good enough. So z sub 0.34 is about 0.41. We found the value from the area. The table read backward.
Same table, just in reverse. Nice.
One last thing worth carrying around in your head. A quick rule of thumb that needs no table at all. For any normal curve, the standard deviation bands always captured the same percentages. About 68% of the values fall within 1 sigma of the mean. That's mu plus or minus sigma. About 95% within 2 sigma, and about 99.7% within 3 sigma. 68, 95, 99.7. True for every bell, whatever mu and sigma are, because standardizing turns them all into the same z.
68, 95, 99.7. Just burn those 3 in.
Let's pull it together. The headline is the bell curve. N of x, mu, sigma. Mu centers it, sigma sets its width.
To find any probability, standardized with z equals x minus mu over sigma. Then read the cumulative table, forward to get areas, backward to get cutoffs, plus the uniform distribution and the 68, 95, 99.7 rule.
And here's the thread into next time. Remember how the binomial histogram, all those bars, already looked bell-shaped?
Oh, I see where this is going. That's lecture 11. When n is large, we use this smooth normal curve to approximate those binomial bar probabilities, plus the law of large numbers. See you there.
See you in lecture 11.